This week we're going to talk about data files, data file analysis a bit, and then we'll go into some exploration of the malware file that I created for the attack that we did on Tuesday. And kind of what I was telling everyone last week was that we'll dive into that without using a lot of like the heavyweight tools that exist. So we'll just kind of look at it as from the perspective of it being a file that we don't know a whole lot about yet. So, and hopefully that'll give like some insight into sort of what the journey is, for lack of a better term, for a lot of this stuff. But I wanted to do this lecture, which is going to be, this is kind of one of my own like kind of personal concepts that I typically put together when I'm talking about malware analysis at work and with some of the communities that I'm a member of. So the big thing is it's data organization. So on a computer system or in the cloud search, whatever, Google Drive, all your data tends to have some sort of somewhat standardized organization to it. Sometimes there's international standards bodies that govern this. Other times there's just de facto standards that are responsible for this. A really great example might be that if I was to format a USB drive on this Windows machine here that we have in class, I could then take that USB drive and I could plug it into my laptop here and I could read all the files and I could copy new files onto it. Or I can copy it, I can put it in one of your Macs over there, and I can do the same thing. And the reason for that is that like the Windows FAT file system, which is a way the data files are organized in Windows, has become pretty common de facto standard way of organizing files. So you're probably familiar with a lot of the kind of functional standards that exist. And so I put the key concepts up here. I think the last one I actually start to reference a specific file type, but that's just because it's so common, so commonplace that you're probably familiar with it. And we're also going to use it for a little bit of the example discussion later on. But basis, you're familiar with file systems. Typically, it's a way of organizing both files and folders within your system. You may be familiar with like programs. Programs are a way of organizing executable content. So the distinction between programs and files, typically for many of you, is that I can run code out of a program, whereas a file is typically something that I read or write. So programs typically contain executable data. So that's a distinction and specialization of the file type. Archives, for instance, they tend to have file systems or file layouts within them. So they're containers, they're folders, for lack of a better term, that contain other files within them. So that's what I go. This is actually a really good one to build off of because it's something that you guys are all probably very familiar with, and honestly, like general purpose computer users are all familiar with zip files being a file that I have on a disk. And then if I double click on it, I get access to all the little tiny files inside of this one big file. So, so you're somewhat familiar with the idea of files as containers. And I just went through the zip file example earlier. The zip container itself is a single file. So if you are on the command line and you dir the content of a folder that has a zip file in it, you just see the zip file as being one raw, flat file. That container, and I'll use the word container a lot of times, it can be conceived as being a big bucket that actually has other files stored within it. In addition to those other files that it has, it also contains a data object that describes how all those files are stored. So if you open up a zip file, if you double click on your zip file, typically in Windows, and it shows you all the files and folders within the zip file, in many cases it hasn't actually extracted any of those or put them anywhere on your file system. You're being given a picture of the internals of that file that allows you to navigate within it, and then you can pull certain files out of it if you want by dragging and dropping. So that view that you're getting is actually described in this data object that's yet another object within that zip file. So it's another almost content within that zip file that also contains the bytes that consist of the image files or the movies or the program files or the libraries that are in the zip file. So I usually like to try and call these things streams, byte streams or data streams. That's an effort to try and separate the kind of container ops concept from the operating system concepts of files, file systems, folders, that type of stuff. So that way, that just helps us not get so confused when we're dealing with things. I can talk about files that I see on my computer, that I see on my system, that I see hosted on the web. But when we're working with analyzing objects and things like that, we can talk about the data stream as being the physical sequence of bytes. Kind of a more generic way that I'll represent the concept kind of in my head mentally. You don't have to do this in C, but I do it in C because that language is pretty ingrained in my background. Because I basically look at it as a byte stream. And I use like the byte type here, but you can use whatever you want as long as you've defined the type definition in C. So in this case, it's a byte. So my byte is probably going to be an 8-bit byte data value or data type. And then this is an array where there's 32768. So it's an array that contains 32 kilobytes or 32768 bytes in it. So those of you who are familiar with C programming language, have written in C, that type of stuff, you could define a type this way. So the stream basically can point to a raw byte array like that. I'll also say that just going back here, I use the array right here just to define a defined allocation. But C still handles this object right here for the most part as a pointer. So it handles it as an address to a pre-allocated sequence of bytes. So you'll see me when I'm going through this use the array and the pointer nomenclature interchangeably this way. So the stream's pointing at a raw byte array. If you're familiar with the concept of typecasting in C, that's basically where you have a raw blob of data somewhere, and you would like C to not necessarily make a copy of it, but you would like C to interpret it in a certain way. And the way that you describe to C, or to any programming language really, how to interpret a block of data or a blob of data is to do something like this that I've got right here, which is you define in this case it's a type, it's a data type, a user-defined data type, or sometimes known as a protocol if you want to go that route as well. There's some programming languages and some books that refer to it as the protocol. So what it is it's this definition here itself doesn't contain data. It merely describes the layout of a raw block of data and how you can interpret it. So in typecasting, if I wanted this stream, somehow I knew that the stream on disk was a zip file. If I wanted to interpret it as a structure of zip data, I might use a construct somewhat like this. And I will be honest, I'm generalizing a little bit here, and we'll get to that a little bit later, but the core concepts here is trying to identify like raw pieces of data and then reinterpret them after you've determined what data they contain. So then that would provide the user with a pointer. So the address that's stored in zip_data and the address that's stored in stream really end up being the same address. This ends up providing the user with a pointer that can decode the raw stream or the raw data in stream using this protocol down here. So let me see, I think I've got, yes?
The pointer that you declare here,
yeah.
zip data, would essentially point to the beginning address of the structure.
Correct. Yep. Yeah, so that means that the first element in the zip data here would start at the 0 byte in the raw byte stream down here, right? And that's exactly what we're getting at, is we're trying to do what ends up being a reinterpretation here. the reason I'm going through all this, and a lot of you are probably very familiar with this stuff, is that this concept will end up being used a lot because you're trying to attack the problem of making sense of data, making sense of streams that you don't actually have a definition for. So you'll be responsible for building up things like this and trying to interpret it. So let me just see. Yeah. Okay, I got this right. Yeah. Excuse me. So going back to our zip file example, all of you are familiar with putting any files you want inside of zip files, including other zip files, if you really wanted to. So in that case, we might actually go and find like the first stream that's stored in this structure here. So there's a list of stream pointers, and so the first of those pointers points to what would geographically be the first stream, or what could geographically be the first stream, the first data stream in the zip file. And again, I'm generalizing here, so I don't have like a whole bunch of the decompress, compress logic that you would expect to see, because I'm trying to just show the kind of container things within other things model that's being built up here. But you can also see that using the pointer that I defined up here, that I basically did a reinterpretation of, that gives me the flexibility to now navigate the raw data that was originally in stream, in the byte array, in a manner that's actually structured. So I can do things like this. In this case, and again, forgive me with the not C compliant string constant assignment here, but pretend that that's a byte copy operation. That's basically giving what the file name is. So you're storing in that object that I said was the directory. Remember, there's the file streams inside of a zip file, and then there's also a directory where there's an object that contains the names of all those files and the placements of all those files. You could line up those indexes with each other like I'm doing here. So the first file is named inside.zip, and then that means that I can then know that the data type within that stream is going to be able to be interpreted as a zip stream. So I'll do the exact same typecasting operation in order to get a direct pointer to the inner stream. So and so that's kind of what we're doing here. So what you're seeing is, I looked at a file, identified the type, wrote a data structure to try and allow me to navigate it. Now I found other contents within that container, and one of them happens to be another container file format. So now I grab its raw data, and then I'm providing its raw data to a pointer that interprets the data structure within its raw pointer, or within its raw stream, in order to provide me nicely structured navigable access to the elements within inside of it, to its contents. Likewise, I picked two file formats that there's a lot of open source information, PDF file and also doc file, so the Microsoft Word document format. Both of those have a lot of documentation on the internet about them, about what their file structure are, what their contents are, that type of stuff. So hypothetically, if you went through all that documentation, you could also create data structures that attempt to represent those as well. And then you could use a similar, you might use a similar casting operation. I'm glossing over some steps here, but you could use a similar casting operation to try and interpret the byte contents within those streams as well, and also get pointers to them that give you structured access to their components. So I kind of like to think of this as the container model of streams. So your goal in looking at a malware artifact, or any artifact that you don't understand yet, is to try and identify what the structure in it is and how to discern what its different contents are. Then your job is to pull those contents out. So there might be like 4 or 5 different components within one file type. You pull each one of those components out and you try and analyze them. They themselves might contain other objects, and you'll pull those out as well and start trying to interpret them. So again, I call this the container model of streams, and use it heavily with a lot of the network detection tools that I've used in the past. So this is where I get to trying to explain why I was throwing in the disclaimer of me glossing over a lot of details before. So many of you are familiar with the zip file format, know that the contents within zip files typically, not always, but typically are compressed, which means you run them through some sort of like deflate or compress operation before you actually write them into the file, which means that if you were to directly read the beginning to end of a zip stream like this into a buffer and then do a cast like this might work. But then each one of these streams are really pointing at compressed data fields, right? So really what you're seeing is that these aren't literally those files. What they are is they are pointers to all, possibly each one of them the same file, all deflated files. And so they have like a deflate wrapper around them. So after you run them through the deflate wrapper, then you get your file and you can go navigate its bytes. So those stages we typically talk about as being parsing. So you want to parse that deflate file in order to get the contents that are inside of that deflate file. So usually what we might do is define some sort of function like this, which is to pull, like in this case, this one might be to pull to decompress and then represent the data as a zip type file stream. So the parse zip file, or parse zip function, excuse me, will take as input one of those one of those deflated files. Its job would be to run an inflate operation, followed by pointing or creating a new pointer of zip stream type to the raw data that it just extracted in memory, and then providing you a zip stream pointer to that raw data, thus giving you the ability to have something that allows you to navigate through the file structure. So you might call something like, you might call it in a way, you might call it in a way somewhat like this. I actually have a typo in this, but that's fine. So there's supposed to be a assignment and then a parse zip. But anyway, the idea here is that you would call this function, giving it this right here, and then it gives you a pointer to your zip stream that then you can apply to, to start kind of building up whatever you're trying to extract the different pieces of a piece of malware. So one of the reasons why I go through all this is that I hinted at this earlier. The reason I'm applying this type of stuff to malware analysis is because a significant portion of malware analysis requires performing what we call black box reverse engineering of suspected malware artifacts. So in a nutshell, what that means is that while up here I actually have a definition for what a zip file looks like, I don't always have, say, a prepared definition of what a particular type of malware looks like or anything like that. When I'm going through it, I actually need to manually build up something like this, and then also build up my parsing function, or parsing functions, maybe multiple, to try and pull out the data contents that are valuable for whatever I'm trying to do. So another way to put it is you'll try and pull out the protocol, or you'll try and yourself recreate the protocol based upon what you've learned from analyzing the malware file. So you'll try and put together a data structure so that you can go and explore the contents of that data structure. So this is where the data structures aspect to this class comes in very handy. And if you did well in that class, you should do well in this class as long as you get over the assembly language hurdles. The big reason for this is that you're going to also build up your own parsing function to pull out the contextually significant contents. So while you can write, given an infinite amount of time, you could write a full parser for any malicious file that you have. Generally speaking, you don't write a full parser. You don't extract the full data into a data structure like that. You end up extracting what I call contextually significant contents from it. So the things that are in the file, the handful of things that are in the file that actually make sense within the malicious context or the actions that are being done. So that said, what I'm going to do is I'm going to jump into looking at that PDF file, but I'll pause for a moment for questions if anybody has any or comments. Okay, so I think I have that PDF. Oh no, it's over here. I have that PDF in here, and I'm going to open it up in here instead of bringing it up in the Windows machine for now. So I'm not going to open it up in the Acrobat reader. I'm actually just going to open it up in a text editor really quickly. One of the reasons for that is, well, you'll see in a moment, is that if I open it up in this one, it actually does a nice job of colorizing the contents. Actually, it might be helpful if before I did that, I did, so some of you may or may not be familiar with this view. So this is, you probably want to become familiar with this, but this is the Linux hex dump tool. There's also a lot of really good ones called like hex view, and I forget which ones are for Windows, but there's a whole bunch for Windows that allow you to look at it. And what you're looking at is that raw data stream that I was talking about earlier, right? So in this case, this is a PDF file. So it was made to be interpreted by Adobe Acrobat. This file format actually has a very public, well-documented standard around it for the most part. I believe there's a few features that might be in versions of Acrobat that aren't as well documented as others. But for the most part, it has a very well-defined structure around it. But the big thing you'll see, for instance, just by looking at the bytes in the file and working off intuition, you'll see that there's a handful of things like this that is at the beginning of the file, possibly trying to tell anybody who decided to look at the bytes without seeing the file name what type of file it is. So regardless of what we name this file, that beginning piece there, that's the first thing you read when you open the file, tells any application what type of file this is. So that's one example of a content, of a structure. That's something that you would put in the file structure, right? Another thing that you'll notice is that there's this, and this is where, and so I'll select like that, although that's a little bit noisy. This is where it comes in really handy for me to jump into the text editor. But there's this 10 obj, and then down here you end up seeing 20 obj, and then down here you start seeing 30 obj, and so on and so forth. So you'll walk down the file and you'll start seeing this pattern emerge. And that's a big thing that you'll be looking for when you're trying to do reverse engineering of files and malware analysis. You'll be trying to look for patterns like that. In many cases, especially when you're dealing with exploits and things, they're designed to be parsable by a known application that would be able to interpret this stuff. So give me 1 second. Sorry about that. So what I'm going to do now, because we're looking at this, this actually is kind of noisy, but you do get to see that you get to see the byte values and everything. This is a useful tool for taking a really quick high density like preview at a file to try and see if you don't know what's in it. This can give you an idea of maybe what type of file it is. So I'm going to go back to the text editor that I had this open in. One of the nice things about the PDF file format is that it is primarily text-based. When we start later on in the course, not too much later on, we'll start dealing with a lot more files that actually are binary, so they aren't going to be very easy to look at this way. But PDF gives you a nice benefit of still being kind of cryptic, but being ASCII or text-based, so that you can kind of make some intuitive judgments about the data structure in here. So like one of the big things is that like it supports white space and things like that. So you have all these different carriage returns and tabs and everything, making it actually somewhat readable to a human. But you can see, go back here and you can see now it's a lot more apparent. You've got like this 1.0 obj and then end obj and then 2.0 obj and then end obj. So you see this more clear pattern coming up, which is it looks like that every time they have possibly different contents in here. And this right here looks like it might be the data bytes inside of that particular component in there, all the way up until you run into one of these. So you can keep going through the file like that and start interpreting that, oh, look, maybe there's 3 contents or 4 contents. So if I consider this to be one content up here, then each one of these are defining other, say, objects within the file directory or within the container directory. So if I wanted to go and analyze this file, I might write something that can walk through and actually pull these things out, right? So let's see. So I might go through here. I start to see things like this stream and end stream as well, which themselves, since I'm using a text editor that actually has some hints in it on how to colorize PDF, those things stand out. They get highlighted green for me. That's also giving me a little bit more intuition about, or I should say hints, about document structure as well. So there's these things called streams as well that I should look out for. So for instance, here's the 5th object. So these seem to all go in a sequence. And then it ends here, and then here's the 6th object, and then it ends here, and then here's the 7th object, etc. And it has some more stuff in it. The other thing that you'll notice is that if we go back up here to these objects, all of these objects seem to have what look like maybe some sort of metadata or programming language or data structure associated with them too. So they all describe something. Not entirely certain what, but I could extract them all and maybe differentiate them in that fashion. Likewise, we get down here and we can see that the object structure, at least this particular object structure, looks very different from the ones we saw up above. So in this case, we get down here to the 7th object, and it has these things that go and discuss something about template.pdf. And then it ends here. And then we have another object that goes and says something about subtype, application, PDF, etc. And it has a number of other descriptions to it as well. And if I keep following it, then I get to the stream word. And we know from looking above, or we learned looking above, I should say, that there is a stream and an end stream up here. So maybe I can look for an end stream down here. And sure enough, when I do, I look at the end stream and I see the pattern as well, end object. So what's going on here, and how the PDF document structure, and this is where I'm going to pull from my knowledge and not necessarily something I just intuited from looking at this today. But what I'm going to pull from my knowledge is that The PDF structure has the ability for you to define objects that are going to be within that PDF. So something that might be a little bit more familiar to you is Microsoft Word documents, right? So if you've ever written a report that, you know, is decently complex in Microsoft Word, you typically have blocks of text in paragraphs or something like that. And those sections of text will have like formatting around them and things like that. You can also drag images into your Office document. You can drag Excel files into there. You can inline Excel files. You can inline other Word documents as well inside of your Word document. So the Word document itself is basically a big container you can stuff all these things into. And then it describes to Microsoft Word how Microsoft Word should lay this out both in memory, which would be a data structure like what I was showing you, but also on the screen, how to present it to you. So PDF is basically the same thing. PDF is a lot more presentation focused, to be fair. And it's also not necessarily designed to be very editable after the fact. So it's generally designed to be a read-only final format type of thing. So all of what you're seeing here is objects that are supposed to be inside of the PDF, many of which are just used to do formatting commands and stuff like that within the PDF. But there are some objects that actually have stream data within them so that they can present things inside of the PDF that you're supposed to look at. And this is one of them, is there's this big stream right here, and that's actually what they use stream and end stream for. So it means that I can go and look for, again, hypothetically, going back to my intuition approach, is I can go in here and I can walk through this document and look for sequences of obj followed by end obj. And then I can also, within that context, I can also look for streams as well. And then I can pull out the stream data and do things to it. What I would intuit from that too is that if I can put some metadata in the object definition, like was done up here, I would guess that data, that metadata inside the object definition before you get to the stream, probably instructs me on how I should parse the data that's in the stream. How I should, what parsers I should write or what parsers I should look for to try and extract it. So, and then I'll get all the way down here. I'll go back down to the end stream, and you can see there's another object down here. And then this object looks like it actually is something containing JavaScript and everything. And so it goes and describes some JavaScript right here. So it looks like there's also some content here as well that doesn't necessarily have to be inside of a stream, that still gets put into the document as some sort of content. So there's a way to get content in a stream, or I should say there's a way to get content into the document using just the metadata, as well as a way to get content into the document using these stream objects. So I'll go down here, and what you're actually seeing here now, let me try this. There, you can probably read it better now that it's not purple. But you remember when we were in Metasploit on Tuesday, we actually had an option that allowed us to decide what text was going to be embedded so that it would show up on the pop-up window that pops up when you try and open this document. This is an example of it right here. Or I should say, this is an example of it. This is literally where it was put right here. Also, if you recall, I don't know if I pointed it out or not, the document, or the info document on the particular exploit that I was looking at said that it worked on English and Spanish versions of Windows XP and Windows 7. And then if you go up here, you can actually see the JavaScript code. And this JavaScript code, in addition to looking at, let's see if I can find it, CD desktop, you can also see there's a Spanish version of here where it says if escritorio exists, then try that if the first thing failed. So, or if exist mis documentos right here, then try to put it in there instead of my documents. Because the author of this exploit, possibly for whatever reason, this might actually inform us of the author's targeting, because they didn't put Farsi on here, and they didn't put, you know, Hindi on here, and they didn't put Japanese on here or anything like that. They only put Spanish and English. Those are their targets. You know, maybe their targets are, you know, the Americas for some reason, where, you know, you have the largest English and Spanish-speaking populations in the world. So that's another, say, piece of content or information that I might pull out of here to try and allow me to inform, say, people I work for, what the purpose of this malware is, what the targeting of it is, what the targeting is not. This allows me to also explain what parts of my company's large global network is vulnerable to it and what parts may not be, that type of stuff. So those are also the types of things that you'll get from out of malware analysis. And then we got all the way down to the end, and you'll see that there's this EOF as well. Now, one of the things I will say is that I believe this actually shows up twice in the file. Yeah, this actually shows up twice in the file. So, but for some reason it shows up twice. Now, I don't know exactly how Acrobat Reader is supposed to interpret that, because I didn't write Acrobat Reader. But I do know, looking at this file, is that there's more stuff past the thing that says EOF. So if I wanted to write something to parse this file, and I was following the spec that might say that I have to stop reading when I encounter this EOF symbol, I know just from looking at this that if I want to analyze more contents of this file, then I need to ignore the EOF signal, or the EOF indicator here, whatever we want to call it, the EOF marker, and actually just wait until I get all the way down to the end of the file. So a really simple approach to this, and I'm going to write something really quickly that attempts to parse it. So I'll just do this really quickly. So then I'll just say like data equals, I'm going to do this in Python because if I did it in C it would take a really long time, and I'm going to do it in the very memory inefficient way of actually loading the entire file contents into memory and then just walking through it as a huge byte array, because that maps with the concepts that I threw up here earlier. So I will not do this as like one, I won't do 5 operations in one line like I normally do though. So we'll call that evil.pdf. So now I'm going to open it. And then what I'm going to do is I'll use this again. So stream equals, you know, file handle dot read. So those of you who are not familiar with Python, I recommend like getting. There's a lot of really good documentation out there. Some of you may have taken the data structures class with like Paul Talega. The Open Data Structures book, there's like a book called Open Data Structures. There's a version of it for Python that works really well. I think it's actually their pseudocode book, because Python's basically that. That'll give you some background into some of the examples that I'm doing. I'm writing Python so that the in-class, you know, walkthroughs can be a little bit easier. And feel free to follow along if you want as well with, honestly, like any PDF file will work this way too. So what I'm going to do is I'm going to load the data bytes into stream. So stream is basically going to be a byte array like I was showing in the slide earlier, which means that I should be able to extract that one content. So what I'm going to do is I'm actually going to create a Python dictionary that's going to be the PDF file. So I'm going to say like PDF file, right? equals a new dictionary. And then what I'm going to do, if you recall, that, let's do this. And I can switch between them easier, so I can use tabs. So if you recall, there's this first thing here, right? That's the PDF 1.0 or whatever. So maybe what I'll end up doing is I'll say like PDF ID equals, or sorry, file PDF ID equals, you know, stream 0 colon, and then we'll say that's like 8, right? So see, there you go. So now I've already extracted like one piece of the file there, that %PDF like 1.0 thing. So, whoops, there we go. So then, what I will do is I might now write a for loop that tries to go through and parse out those different object and object things, right? So maybe just try walking through. Actually, just I can probably do this with a find. So I would do like stream.find, you know, I think it was like 5 space 0 space obj, and I didn't actually see any objects where the second number wasn't 0. So if I look for like this, so this is me going through and right. So now it's telling me that at the 11th byte in the file, there's an object marker, an obj marker. So let's find out if that's true. So that would mean if this right here is byte number 8, then that would mean that 9, 10, 11, right? And then that's space, because that was the first thing I was going to, that I was trying to mark on, was the space, followed by the 0, followed by another space, followed by O, B, and then finally J. So we managed to figure out a way to identify where the object markers begin and where they end. So what I might want to do then is I might just want to expand this data type definition a bit. So what I'll do is I'll create the PDF ID right here, and I will force it to be an empty string so that we know that if it wasn't populated down here with the right data, if for some reason that failed, then it would be empty. So the next thing I might want to do is I might want to put in objects and then set them to be a list. And what did I, oh, sorry, I'm used to typing up in JSON sometimes. So what I'll do then is I'll get the first stream and then I'll say while like obj I does not equal -1, because if we run pydoc string.find, it's going to tell us that if it ever fails, it's going to return -1. So if it cannot find what you're looking for, it's going to return -1, which means I can use that as like the, you know, as the terminal case or the exit case in my while loop. And I totally did this like that. So what I'm going to do then inside of the while loop is I want to, let's go back to the file a second and look at this, obj. So we'll go through each one of these. Each one of these seems to have seems to have some sort of, in this case, Control M character after it. And this is me. I'm walking through all the occurrences here because I'm trying to build up in my head what the pattern is that I'm trying to extract from this so I can build some more data structure into it, right? So looking through this, every single one of them has the Control M character, and I forget what that is, but what I can do is I can do the hex dump again to try and see it. And what it is it's actually this one right here. So it's 0D is the character. So it's also always one character after the match string. So that means that if I really want to, I know that I know this is true. So obj begin, or I'll say obj start, is equal to, this will be an index variable, so obj start is equal to the index of the match string plus length of the match string plus 1. Because in addition to that match string, there's that extra character OD, or whatever that is, 14, that I also want to skip so that I can get to the first byte that's in the object. And then, if we remember, there's an end object after that too. So I would want to do obj end equals stream.find end obj. And now this is where I'm going to do PyDoc again because I can never remember the syntax for this, and also so that you all have it. So what I do is I can give it a start and an end, which means that it can either start looking at the beginning of my string, so at character 0, or I can have it start looking after a certain point in the file and never look at any point earlier than that. I can also have it end before it gets to the end of my string. So in my case, I only want to look for the end obj to be following the current obj thing. Or really, I just want to look for where it happens after that obj start that I already initialized. So I put that over here like this. And then I can say obj data equals stream obj start obj end, like that. And then what I'll do is I'll put it in here. So I'll say, I'm going to kill that. I'm going to say obj, my bad, PDF file obj dot append. I'm going to put a new object in there, and I'm going to say length. Just for the heck of it, I'll just say length. So you can see some metadata in there. Is going to be obj end minus obj start, and then data is going to be obj data, like that. So, and then finally, what I can do is I can try printing this stuff out, like this. Oh, sorry. I don't need to use the length function if I'm already doing integer arithmetic. So now it's going to go through and let's see what it does. Oh, two guesses what I forgot to do there. Anyone know what I forgot to do? I forgot to, I forgot to advance the cursor. So I'm maintaining this cursor right here. So I ran this outside of the while loop. I need to run it starting from the end of my object now. Whoops. And then we'll just put it, say, after obj end. So obj end. So, and then there you go. Now it piped out the data structure. What I'm going to do is actually can't remember if this is it. I'll just do this. I think I have JQ. Oh. Okay, never mind. Like that. Sorry. So basically what you're seeing now is that there's an object length 40, its data is right here. Then there's an object of length 53, and its data is right here. Then there's an object of length 221, and its data is like, goes to here. Object length 40, length 25, length 28, and then finally there's one that's like length 44.210 or whatever. So what I've really done here has been to write a kind of object parser for the PDF. And I've done it not necessarily based upon a whole bunch of like internal knowledge I got from analyzing the PDF specification. I've really gotten it just from looking at the file, trying to identify the different patterns that are in the file like that, and trying to rebuild at least what the structure appears to be to me. And I will say there are a number of cases where what I did there is going to fall down. A really great example of that would be the case where they use a different secondary number. So if you remember here, all these objects always had 2, 0. If for whatever reason there was a more advanced PDF that actually used a different, a different number there, for whatever purpose that is, I actually don't remember it off the top of my head, then that would cause me not to be able to match the objects that didn't have that particular characteristic in them. Another thing that might happen is just like in Microsoft Word documents, you can store a Microsoft Word document, you can drag it into another one, and you can have a Word document inside of a Word document inside of a Word document, like ad infinitum. You can do the same thing with PDFs. So if I happen to have a PDF file in here, then my parser is going through and it's going to pull out the objects inside of that PDF file as well as the one that I'm looking at. And then you just have to ask yourself whether or not that is actually a bad thing or a good thing from your point of view. And that all depends upon the context and depends upon what you're trying to achieve. So I'm going to open this back up again. And one more thing that I was going to do was I was just going through all of this. Was just I was just going to show the end of it also, just to show you. Typically has like this stuff as well. So it says like xref. And there's an xref table in here, and it says something to do with the object relationships within the file or something like that. Again, I can't remember exactly. But it's more metadata, so similar to how we had that we discussed in a zip file, there's that directory with your files and everything in there that is itself a data object that you need to consider. This one has some other data objects that are part of the overall document format that you also have to consider. So, that in a nutshell is my super simple, half-hour, quick and dirty PDF parsing tool that will allow me to extract the individual objects from many PDFs. And then if I can do that, that means that I can then do something like this, like parse PDF object. Or I can have it out here where I don't do this, and then I do like for, in, we'll say PDF filed, what did I call it, OBJ. So I can do something like that more or less. This thing's going to get mad at me because I never made a parse PDF object function, but if I wanted to, I could do that. So, and this is kind of how the type of thing starts, or could start. Again, generally only take this type of approach if it's dealing with a file format that you're unfamiliar with, or perhaps a section of a file that you're unfamiliar with or you don't have a parser for. Again, really great example of this is malware tools, backdoors that are put together by adversaries where they have custom tools that you may not have access to. So I will also, I think I have it down here actually. There we go. So I also have this tool, and I will show you this right here. So this is this guy's blog. So this guy, he wrote a tool, I don't know how long ago now, like maybe 9 years ago or 8 years ago or something now, that he called PDF Parser. And this has been a really popular tool for doing a lot more advanced version of what I was showing you. And it's been built up over the years, not only informed by the PDF specification as it's as it's built, or I should say as it's documented, but also built up through the kind of gathered collective wisdom of like the security community as well. A really great example is that the PDF spec says one thing and a number for how the document should be written. What happens when your document has slight errors in it or slight flaws in it, stuff like that? Do you want your parser to refuse to try and parse the file? Or do you want your parser to try and guess at what was intended by that mistake and then interpret the mistake in the most likely way it was intended to mean, and then continue moving forward to parse the rest of the file? We see this a lot, and even Acrobat Reader has a decent amount of, I would say, fault tolerance built into it, where in some cases a document that doesn't exactly meet the spec can still be presented to you. And that benefits the end user experience, but it also makes it a lot more difficult for somebody who doesn't have access to the Adobe Acrobat source code to be able to write a parser that can pull the data objects out and analyze them and basically give you a better view of what would happen if it were opened in Acrobat Reader. So this is a really useful tool. What I was going to do was I was actually going to go through some of the features. And also there's I'll do another tool too. So and these are libraries as well, or I should say they can be interfaced as libraries as well. So there's another program that's called ExifTool. It's this thing, it's like a Perl library. And it's a Perl library that was originally intended to extract all the metadata from images. So for images, in addition to the pixel data, whether it's compressed or uncompressed, a lot of times you have other metadata in there as well, like what kind of camera took the picture, when it was taken, time. Some of them have geographic coordinates or GPS coordinates embedded within them. Others have maybe the lighting information that was the camera was able to ascertain from the environment and things like that. Who knows? There's a whole bunch of different formats But then some people in the community said, hey, this is a really great tool for doing that. And it organizes the data really well. There's a whole bunch of other non-image file formats that also have a large amount of metadata. So a great example of that is in Windows, if you've ever right-clicked on a file, like a document or a program file, for instance, and then you've selected properties, a lot of times it pops up a window that shows you the file system properties, like permissions and things like that. There's also a lot of times like a version info tab. And the version info has information like the author, the company, the version number, stuff like that. All of these metadata fields that are actually embedded within a version info structure inside of the EXE file or the DLL file if you're using a Microsoft Windows library. So they said, hey, that information is all really useful to know. What if we just write plugins for this tool that extract that data too? So now you have this tool, so if I can type right, oh, okay. Let me just see. Oh, it's mad about this thing. But that's fine. I will just think I can load up the Kali VM and I can see the same thing. It happens to be broken on my system, which happens from time to time. I'll fix that. It's probably because I just installed it from the system packages. But I believe Kali has a copy of this tool as well, so I'll just load up that VM. And again, this is a great example of why heavily utilizing the suspend feature in VirtualBox is very useful. So I also don't have it on here either. But okay, well, whatever. We can. I'll fix this and make that available for later. Instead, I'm going to go back here and do the PDF parser tool. So for instance, what I can do is I can do A, which is I'm going to pull this one, display stats of PDF document. So it's got these stats, so it has maybe the number of comments that are in it, the number of xref, the number of start xref, the number of trailer. So from what I can tell, this is the number of times that each one of those commands are actually used. So this thing's gathering some metadata from analyzing the document that might be useful. For instance, I mentioned earlier that there was 2 copies of the EOF tag. Maybe it's uncommon for a PDF that was built by a normal tool that you use for business to have this happen twice. Maybe that's only common to have happen once. It has a list of indirect object number 12 for some reason. That tells me that maybe I should look at that object in particular. So maybe I do 12.0 obj. Oh, it's not even there. So maybe it's not there and that's what's weird about it. Yeah, there's, no. So, yeah, there's object 10 right there is this JavaScript. And then for some reason, it starts over again with object 1 and then object 3 over here for some reason. So, I don't know. The other thing too is, let me go back here, parser. There was also this, where did I see it? There was the stats, and then there was another one here that was like, yeah, -c content. So this one's kind of doing So this is kind of doing what my parser that I wrote in Python was doing. This one's doing it a little bit better, where it's actually getting the number one, I guess. We'll go back up here and look at the description again. So this is the one I'm looking at. It says, display the content for objects without streams or with streams without filters. So that tells me that there's a concept in this file called filter that I should also look for that might be a parsing consideration. But it's also saying that objects with streams and objects without streams are two special cases that I might have to handle individually. There was another one in here that was also useful. I'll go all the way back up here to the top and say, so here's a good example. Pass stream object through filters, and there's flate decode, ASCII hex decode, ASCII 85 decode, LZW decode, run length decode. So there's a whole bunch of different filters, and judging from the naming here, they're all different types of compression filters. So maybe if I go in here and I look at the evil.pdf again. So I'll go down here to the stream. So there's that stream which doesn't really have much in it and is actually listed as like a length of 0. But there's another stream down here that was particularly interesting, and if we go back over this, you can see there's a size number here, the 73,802. There's a checksum to it, so it actually got checksummed, and that's recorded in here as well. That's probably a way for it to identify if an object is actually broken or not, allowing it to maybe do some sort of runtime correction or at least like runtime hiding of that. You can also see that there's the filter. So it tells what kind of filter is in use, and it says flate decode. So for instance, in this particular one, maybe I'd want to extract that. And then finally there's a length, 44058, so 44058. Length actually shows up here, or I should say size shows up here twice. So there's 73,000, and then there's another one that's 44,000. This leads me to conclude that maybe one of them is saying how big the compressed data is. The other one's saying how big the data should be when you decompress it, when you deflate it. For instance, the deflate operation is going to need to know how big of a buffer needs to be allocated. So this is object number 8, I guess. Oh, whoops. Let me not throw stray data in here. So let's go back here and look at the options here. Here we go. So file name to dump stream content into, object to select. So maybe I can do Python. Right, contains stream. So then there we go. And see, there's all that stream data. So I just have something now. This parser allows me to extract the contents of those streams. So then, let me do one more thing. So if you remember, I can run it through a filter. So let's try running it through this filter, right? And whoops. What is this thing? So -F. I should probably read whatever is going on here. I don't know. Oh, that's the problem. Maybe? That might be the problem, I don't know. Well, let's see what happens if I do this. I might be doing this wrong. Oh, maybe it doesn't take this. Oh, that's what it is. So you can see this thing is actually showing the content right here. So maybe what I'll do now is I'll do -d food deflate dot stream, right? And there we go. Now you remember that the size of it was listed as 73,802, and that seems to match what we got out of there, which gives us a good amount of a feeling for how this thing has been, has been decoded probably correctly. So now what we see is another type of file. And what this type of file is actually a Microsoft Windows executable file. It's a Microsoft Windows program. So inside of that stream, what was compressed in there is actually a Microsoft Windows EXE file. What I can do is look around in here, and I might actually be able to find some information as to what's going on in here. Typically, a EXE file has executable data in it, right? And then it also has a bunch of memory data, so data on how to tell Windows how to set up that program's memory space, so that when it loads it from disk, the program has all of the necessary dynamic space allocated for it. In addition to that, it also has data intended to present information to the user as well. So you can see all that here. And that's basically what you're seeing here, is a whole bunch of what amounts to message data as well as some network related data as well. Those of you who, for instance, have taken the computer networking course here might recognize some of these headers as being headers that are common with the HTTP protocol. This leads me to conclude that the EXE file that I just pulled out of the PDF after I started hammering at it contains some sort of code that's supposed to talk over HTTP. And that's weird and concerning. And that's also something that I can help inform, say, the people I work for about. So that said, I'll end the lecture for today on that note. It's a good stopping point. So do I have any questions or comments? Yeah.
So like with a PDF, you obviously have ways of knowing what it is with other file types. But if it's like just a bunch of bytes, like what do you just try and different decoders on it, like base 64 codes, so you can start getting to something you recognize or whatever?
Yeah, so you'll, and that's the thing. So here we'll do this. This one's EXE file, but it actually looks a lot more like a mess than the PDF does, right? So, and also when I pulled it out, I didn't happen to know what it was. I didn't know that until I looked at so I'll look at this file, and I know that in Microsoft Windows, that MZ happens to be the 2 bytes that are at the beginning of every single Microsoft Windows EXE. A Linux program, a Linux executable program or library, a shared object library anyways, has a similar, begins with a similar sequence of bytes. I think it's usually ELF, unless you're using some weird version of Linux. And then basically, for just to kind of give you a hint, since Microsoft Windows is heavily into legacy reuse, what they basically have is a little bit of header data and then some 16-bit code that's right around here. I don't remember exactly where it stops, but it's somewhere around here. It's basically 16-bit code that if you try to run this program from the DOS command line, it would emit this string here. But really, what it also has is embedded in this data here is I think there's a reference to this, or I think it's actually down here, is a reference to where later on in the file the actual Windows 32-bit or 64-bit code lives. So there's actually a table here that explains to Microsoft Windows when you're loading it up in the GUI part of Windows where to go and find all this stuff. Where to, and that's also what this stuff is down here as well. So for instance, the .text that's right there, that's actually giving the name of, and then I think somewhere around here too, I'd have to, there's a lot of tools that'll go and explore that for us, but it also tells us where in the file to go find the executable code. So Windows interprets that, which means that anybody who wants to get an EXE to run executable code on Windows needs to always adhere to that standard as well for the most part. So, yep.